Standard medical imaging relies on a blunt physical compromise. Deep penetrating modalities, like X-rays, require high-energy ionizing radiation. Because they map bulk tissue density, they easily render bone, but they often struggle to provide clear contrast for soft tissue. Across the electromagnetic spectrum, exactly between microwaves and infrared light, sits the Terahertz Gap. Spanning 0.1 to 10 terahertz, its defining feature is extremely low photon energy. At 1 terahertz, it delivers just 4 milli-electron volts, a fraction of the massive electron volt payloads from X-rays. Because the photon energy here is so low, terahertz radiation is entirely non-ionizing. It lacks the power to knock electrons out of orbit, meaning it cannot cause DNA damage or cellular destruction. Exploiting this low energy gap offers a method for high-contrast biological inspection without the biological toll. But accessing it requires solving immense engineering hurdles, specifically figuring out how to successfully generate and detect these elusive waves. The engineering solution that emerged to harness this gap is Terahertz Pulsed Imaging, or TPI. Standard optical or X-ray imaging techniques rely on incoherent detection. They simply measure the final intensity of the light or radiation hitting a sensor, discarding all other wave data. TPI abandons that approach. By utilizing coherent detection, TPI allows us to map both the exact water content and the structural geometry of tissues completely label-free. To do this, coherent detection requires the system to record the full temporal profile of the electromagnetic wave's electric field, rather than just tallying its total power output. To see exactly how TPI extracts the specific sunctional data from a biological sample, we have to look under the hood and deconstruct the hardware architecture of a terahertz time domain spectrometer from first principles. The foundational power source driving a TPI system is a femtosecond laser, typically operating at a wavelength of 780 nanometers. The initial laser pulse strikes an optical beam splitter, dividing the light into two distinct, highly synchronized paths, the pump beam and the probe beam. The pump beam travels through a series of lenses to reach its primary destination, an emitter photoconductive antenna, or PCA. Inside the emitter PCA, the laser pulse strikes a semiconductor, generating charge carriers. A static bias voltage rapidly accelerates them. This sudden acceleration acts like a spark, emitting a broadband terahertz pulse into free space, directly toward the biological sample. Generating the terahertz pulse is only the first step. Capturing the multi-dimensional biological data hidden inside that pulse requires the precisely timed arrival of the secondary light path, the probe beam. After passing through the sample, the altered terahertz wave arrives at the receiver, the detector PCA. Unlike the emitter, this detector has no external bias voltage. It functions as a closed switch, gated open only by the exact arrival of the secondary probe beam. A mechanical delay line alters the probe beam's path length. Moving it on a micrometer scale shifts the beam's arrival time at the detector, allowing the system to sample the terahertz electric field piece by piece, mapping its exact amplitude across the time domain. This is very different from taking a simple photograph of light intensity. The system is physically reconstructing the exact morphological shape of the electromagnetic wave as it unfolds over time. Capturing this temporal electric field defines the entire TPI process. It allows us to mathematically decouple the wave's amplitude from its phase, providing two independent sets of functional tissue properties from a single pulse. When terahertz radiation interacts with biology, the frequencies resonate perfectly with the intermolecular vibrations inside the tissue. Specifically, the hydrogen bonds in liquid water are highly responsive and absorptive to these waves, soaking up 220 inverse centimeters of radiation at 1 terahertz. Passing through this water-rich environment alters the terahertz wave's shape. Capturing the full electric field lets us extract two distinct data paths. The first analyzes the vertical drop in the wave's peak amplitude, allowing us to calculate the tissue's broadband absorption coefficient. Biologically, a high absorption coefficient indicates a high local water content or an exceptionally dense tissue structure. The second path analyzes the horizontal time delay in the wave's arrival, which measures its phase shift. The phase shift is used to calculate the biological target's complex refractive index and establish time-of-flight depth profiling. By splitting the data, a single terahertz pulse yields two independent medical maps. One tracks chemical hydration, and the other tracks structural geometry, all calculated directly from the wave without relying on complex Kramers-Kronig mathematical estimations. We can see exactly how this absorption data translates to the clinic by looking at oncology. During tumor progression, aggressive cancers like brain gliomas require heavy biological resources, inducing a localized increase in blood supply. This increased vascularization creates a concentrated anomaly in the local tissue's water content. This chart plots the absorption coefficient against frequency in rat brain tissue. The data shows an elevated curve for the tumor region, diverging sharply from intact tissue. That hydration gradient also affects the speed of light. Looking at the refractive index, we see the exact same upward divergence spiking within the tumor zone. Together, these dual metrics create a high-contrast, label-free marker. TPI maps invisible tumor margins purely by detecting the localized water accumulation driving the cancer's growth. Beyond soft tissue hydration, the time-of-flight phase data excels at mapping hard tissue structures, particularly in dentistry. Consider the composition of a human tooth. The outer enamel is approximately 99% mineral, while the underlying dentine is roughly 70% mineral. This sharp transition in mineral density gives the two layers vastly different refractive indices. When a terahertz wave hits this internal boundary, a portion of the wave reflects back to the detector at a different speed, creating a clear time-of-flight echo. By timing these echoes, the TOF data accurately stratifies the internal architecture of the tooth layer by layer, revealing its hidden geometry. This exact geometry is crucial for detecting underlying pathology. Dental caries begin as microscopic zones of localized enamel demineralization. This loss of mineral alters the tissue's interaction with the wave. The absorption coefficient of carious enamel is typically 35% larger than healthy enamel. By combining the structural depth map with the absorption data, the system precisely highlights the otherwise invisible carious lesion. However, this exquisite sensitivity to water comes with a strict physical constraint. Because the human body is roughly 60% water, incoming terahertz signals are rapidly absorbed and attenuated on the very tissues they are meant to scan. As a result, terahertz penetration is physically restricted to a few hundred microns in fresh, living tissue. Imaging targets superficial skin structures, specialized endoscopic probes, or ex vivo surgical assessments. Despite these penetration limits, the underlying technique holds immense value. Coherent terahertz time domain spectroscopy successfully captures the invisible hydration gradients and structural boundaries of human tissue, transforming them into quantitative, high-resolution functional maps.